Hello, I'm Jiarui. I'm going to talk about our work on hijacking attacks on UAV follow-me system in realistic scenarios. So the outline would be the following. I will start with motivation and background. Visual object tracking is a vital component in unmanned aerial vehicle, and this system has been widely applied to surveillance, infrastructure inspection, and photography. Due to this wide application, a compromised tracking system can lead to significant consequences such as loss of vehicle or even conducting incorrect operation on the false target. So our work studied the realistic challenges of hijacking a physical UAV system during its visual object tracking algorithm. And our findings are an attacker can use some physical approach to inject malicious signal into the gimbal camera to cause more successful hijacking attack. So UAV visual object tracking system deploy various tracking algorithms. Among them, multi-object tracking algorithm has seen many success in autonomous systems. Thus, we focus on this type of algorithm in this work. And existing attacks against object trackers, multi-object trackers, they either only work in digital space or on autonomous driving scenario. And other security research on UAV system focus more on the sensor level. So we think there lacks a systematic security analysis of the complete UAV application pipeline from what's the attacker's capability to perturb the sensor and how that error propagates into the system and eventually cause application level failure. So in this work in progress, we characterize realistic challenges in hijacking a UAV operating follow-me application. So existing work has shown that an attacker can execute an optimized trajectory to cause an ID switch in the object tracking algorithm. But doing that against a physical drone that is operating and that's fine and operating in follow-me application comparing to a static camera in realistic context introduce a lot more challenges, including physical constraints such as the separation between the victim and the attacker, and also real-world uncertainties where the victim can have motion response to the action of the attacker, and also the environmental factors that naturally exist when in a real setting. Also, system latency is another thing to be considered because the attacker needs to run 3D detection and attack optimization in the pipeline, the attack pipeline. So the figure on the right shows a high-level idea of our attack. Basically, in a benign scenario, the drone will follow the victim, and during the attack, the attacker will walk into the view following an optimized trajectory, and after it, due to the executed trajectory, there is identity switching in the object tracking application, and thus the drone will follow the incorrect target. So in our threat model, we consider the main goal is to optimize and execute a malicious trajectory. And the attacker will be able to know the algorithm deployed on the drone without knowing the actual model parameters. So this is a gray box setting. And the attacker will also be able to know the product line or the model of the UAV drone so that it can know the configuration of the camera. And the attacker will have access to 3D detection sensors such as LiDAR, radar, or depth camera to run real-time 3D object detections. So we put the existing algorithm to our more challenging scenario, mainly in terms of adding the knowledge of UAV pose and gimbal orientation, and also we adapt the optimized trajectory to realistic motion to constraints. So our main algorithm is an iterative process, an online iterative process, where in each time step there are 3 main steps. First, the attacker will do a real-time 3D detection to know all the location of all the object of interest, including the victim, the drone, and the attacker. And then, based on the knowledge of the location, it can calculate the extrinsic matrix of the camera, and also based on the configuration that we know in prior, it can also calculate the intrinsic matrix. Thus, we can project the 3D location into the 2D camera view. And in the attacker machine, you can run a surrogate tracking algorithm to know the state of the system. And based on that, we can run gradient optimization to calculate an optimized trajectory. So to evaluate our hijacking attack in real scenarios, we perform experiments on high-fidelity physical simulator gimbal, and we use the open-source UAV control software PX4 Autopilot. We implement our Follow Me application using SORT algorithm, which is a representative multi-object tracking algorithm, and also image-based visual servoing with PID control, which can generalize to different UAV platforms with resources constraints. So we mainly consider following scenarios, like for physical constraints, we enforce a minimum distance between the victim and attacker, and victim response, we use a pedestrian motion model, and wind level for uncertainty, and also we inject systematic latency and detection error into the attacker's optimization pipeline. And yeah, the QR code is for the video. If people are interested, you can scan. This is a successful trial that we selected from our simulation, demonstrating how our attack works in the simulator. So we have a few key findings. First of all, we're interested in we found some factors that significantly decrease the hijacking attack success. So enforcing the separation, like the larger separation between the victim and attacker, drops the attack success rate significantly, because this limits the capability that the attacker can fully execute the generalized trajectory. And also system latency in the attacker's optimization pipeline, and also the 3D detection error in attacker's optimization drops the attack success rate, because the generated trajectory is less optimal for the current scenario. Surprisingly, we find that the instability in flight control introduced by the wind actually increases the attack success rate significantly as we go up. We think this is because this creates errors in tracking algorithm that opens up more opportunities for successful ID switch that softens the impact of the physical separation, physical constraints. And with that understanding, we perform further experiment to see if the attacker can leverage the knowledge to execute more successful hijacking attack. So when injected attacker-induced oscillation into the gimbal 3 degrees and 6 degrees separately, and we can achieve at maximum 95% attack success rate. And in our current physical experiment, we have achieved by emitting acoustic signal towards a DJI commercial drone, we have achieved more than 20 degrees of oscillation. So our conclusion is that by using acoustic signal to induce gimbal motion, the attacker can execute a more successful physical hijacking attack in the real world. And also the QR code is for the video that we perform physical impact on the DJI gimbal camera, and we show that we can achieve large oscillation in 3 different axes of the gimbal camera. So a few takeaways. Firstly is hijacking a UAV visual object tracking system in the real world involves a lot of problems to be addressed in the attack design. For example, physical constraints, uncertainties, and latencies. And attacker can leverage acoustic signals to inject malicious motion into the gimbal camera to achieve more successful hijacking attack in a UAV scenario. So in the future, we aim to analyze the security of UAV visual object tracking system driven by different visual object tracking algorithms against this acoustic injection attack, because currently we're evaluating on one representative ones, but there are a lot of other possibilities due to UAV platform heterogeneity. And secondly, we want to improve the attack design so that we can take into consideration of the 3D detection error and latency in the attack pipeline. And that's all. I'm happy to take questions. Thank you.